Hello, my name is Renzo Huber and I would like to present the software suite called LayNii that is dedicated for analysis of layer-dependent fMRI. This software has been initialized with the great help from the AFNI team while I was working in SFIM supervised by Peter Bandettini and is further being developed now here in Maastricht while I'm supervised by Benedikt. Faruk Gulban has fundamentally restructured, professionalized and augmented the software suite while being advised and inspired by Goebel and his tools. The algorithms implemented in LayNii have been validated and tested by many collaborators, for example Konrad Wagstyl from UCL, Shinho ISMRM, Jozien Goense and Morgan Nils Nothnagel from Glasgow, as well as data from Joop van den Hurk in Scanexus. I have nothing to disclose with respect to this presentation. LayNii stands for Layers and Nifty. It's written in C++ and easily applicable in Linux, macOS and Windows. Installation instructions, example pipelines, as well as tutorial videos are listed on GitHub. The reason why we've developed LayNii is coming from the challenge in layer-dependent fMRI that we have very high quality requirements for the analysis, still while working with these messy, non-standardized data. So for example, the high resolution in layer-dependent fMRI is often only achievable within acceptable speed by using these small field of views that do not fulfill the common topology requirements of mesh-based layerings, namely having kind of closed surfaces without holes. And without these requirements, smooth surfaces are usually not well defined and we end up with unconnected spots as seen here. So we need tools that allow us to work with such messy data. Another challenge is what I call the beer-wine dilemma. Namely, in the encoding limited regime of submillimeter fMRI acquisition, we are usually limited by participant-specific MRI artifacts so that the acquisition protocols are commonly highly optimized for the goal in a given study, and the data cannot be easily pushed through the pipeline that has been developed for another study. So while conventional fMRI, representing the beer here, has been standardized over decades to give you data that are homogeneously be pushable through standard pipelines, like done by multinational brands of beer corporation, this is not really doable with layer-dependent fMRI representing the wine here. There we have specialized data and specialized study protocols and challenges that need much more interactive flexibility, quality control, especially in these early days of the field. So like wine, you get the best quality by not homogenizing your data to be pushable through Henry Ford-like assembly line production, but rather we need flexibility across like regions and years for wine or the data types that the user is working with. So we need layer-dependent fMRI tools that allow a flexible balance of user interventions on one hand without the danger of biasing your data on the other hand. Furthermore, in layer-dependent fMRI, unconventional non-bold contrasts like VASO or Vapor are being popular, which consist of these control label images that need to be dynamically sorted without the danger of noise amplification. So we need convenient tools for those too. And last but not least, layer-dependent fMRI data are also particularly challenged by low bandwidth artifacts and the very low SNR, which needs to be addressed somehow during the analysis. So these are all layer fMRI challenges that most software packages have never been built for. So I would like to show you now some of LayNii's example programs to address these. I guess one of the most popular features in LayNii is the layerification of small field of view data in voxel space. So here, for the sake of validation, tested on a small field of view section of ex vivo visual cortex. And at these very high resolutions, you can see that the equidistance layering kind of underestimates the curvature of the stria genari. Thus, LayNii conveniently also spits out the equivolume layering that fits the stria genari quite nicely. Another example of validating LayNii's layerification here is the 100 micron whole 3D big brain dataset, again showing that at these ex vivo resolutions, the equivolume layers fit the histological layers quite nicely. Another core program in LayNii is the columns generation by means of iteratively dividing the 3D voxel ribbon, allowing the user to unfold and flatten a cortex without interpolation of vertices, but as a direct voxel intensity remapping, which can be very useful to depict topological fMRI data like the somatotopic arrangement in the sensory motor system. So here taking the central sulcus as a two-dimensional voxel grid, which then can be used to flatten it orthogonally across layers and sulcal depth to ultimately end up with a 3D nifty volume of layers and columns completely orthogonalized. LayNii also contains deveining tools using model-based approaches to minimize training vein effects of gradient echo bold data, using previously published formalisms to convert the superficial bias in gradient echo bold to make it look more like non-bold contrasts. In cases where you can assume that neighboring voxels and neighboring columns have very similar layer activity, layer-specific smoothing without signal leakage across layers can be very helpful to deal with the noise level of individual runs. And with this, I want to thank all the co-developers in the author list, as well as all the other contributors, idea givers, and supporters and bug hunters listed here. Many application examples of LayNii can be seen across many ISMRM abstracts this year. Here are my favorites. More information about the software can be found on the preprint or more casually explained on these blog posts.